started. So get up here. Let me begin with a word of prayer. Dearly Father, we thank you again for the opportunity we have to meet and study your creation. Help us to glorify you what we do and to understand a little bit more about calculus today, Lord. In your name I pray, Lord Jesus. Amen. So let's see, before I forget, let me tell you guys the list of problems for Mission 10. So 362, 363, 364, 368, 369, 371, 381, 382, 386, 387, 388, 389, 390, 391, 394, 395, 396, 397, and the final problem for the semester, 400. There we go. So I plan to collect those ones. I think if you do those, you should have a pretty, pretty solid grasp of the material when you finish them. So we've talked about a good part of what you need to do those problems, but not everything. So here, I'll do the first problem for you. All right, so here's problem 362. So example 1, we've got the current is dq dt. So this is a problem from circuits where Q is the charge. And like specifically you're talking about like a circuit where really envisioning the charge that's flowing past a particular point in the wire. Anyway, we're given that I of t is equal to 10 times 1 minus e to the minus 2t. All right. And we're supposed to find net change in Q over the interval 0 less than or equal to t less than or equal to 3. All right? So let me show you how we do this. So one of the applications of the fundamental theorem of calculus is what's called the net change theorem. So the net change theorem, as it's sometimes referred to, is what it sounds like, net change theorem. It simply says this: if you integrate the rate of change of y, like dy dt, from say t1 to t2, you get y of t2 minus y of t1, which of course is the change in y. So the net change theorem simply says that if you want the net change, integrate the infinitesimal change over the time period you're interested in. So if I want the net change in the charge over this time, I'm trying to calculate the change in the charge, I simply integrate from time 0 to time 3 dq dt. But the thing is, dq dt has a special name. dq dt is what's called the current. All right, the current. And so I have to just integrate from 0 to 3 of 10 times 1 minus e to the minus 2t dt. Can you guys tell me how to integrate that? I'll do the easy part out. I'll pull the 10 out. Right, what's the antiderivative of 1 minus e to the minus 2t? I'll do the 1, t. I took it from you. Now you got to do the other part. What's the antiderivative of minus e to the minus 2t? 1/2 e to the minus 2t. I think we have a winner. Because if I differentiate that, chain rule pulls out a minus 2. Minus 2 over 2 gives me minus 1. Hooray. That's what we want. So there you go. That's the antiderivative. We evaluate from 0 to 3, as usual, FTC2. And so that gives me 10 times 3 plus 1/2 e to the minus 6, I suppose. And then minus 10 times, well, 0 plus 1/2 of what's e to the 0? Well, e to the 0 is 1, so that's just 1/2, yeah? And so whatever that works out to. Looks like 30 minus 5 is 25 plus 5 e to the minus 6. So e to the minus 6 is super tiny. This is very close to like 25, all right? So if you take physics 232 here, this is the kind of problem you might see there. Let's see here. So let's look at some other problems here. I just warn you in the homework, just like looking through it, there's some problems in the homework where the problem itself has a definition of something, and you just have to work with that definition and calculus to solve the problem, all right? So I'll let you guys read the homework problems. You can ask me questions about them tomorrow if you got them, all right? So let me move on here. So example 2. What I'm going to be focusing on today is problems that involve solids of revolution. So what's a solid of revolution? So it's like, let's see here, something like this maybe. I take, let's say, this triangle, let's say that the top is y equals to x over 2, and it goes all the way over here to 2, right? So that would make this point what? What's that? 2, 1? So you're saying the y coordinate was 1. I agree. All right, so that's a region, right? And then we could ask what's the volume if we take that area and we rotate it, say, around the y-axis. So can you guys kind of visualize that? So, I mean, I can try to draw a picture. It just never goes well when I try to draw a picture like this. But this is one thing that would get rotated over to here. Now, some people try to draw these like ghostly rotated pictures on top of the graph, but I'll just draw it down here. What we're talking about is something like it's got, you know, flat exterior sides, right? And it kind of has got a cone on the inside, yeah. So something like that. How do you calculate the volume of such a thing? Well, one way we could do it, right, would be to chop it up into washers. We did a lot of that before. I guess I can do it again. So let's use washers. So here's what the washer would look like here, right? So down here it would be something like well, there's no line there, but all right. So I don't know. It's kind of hard to draw it superimposed on the other thing, but it doesn't really matter if you can draw the picture exactly. What's important is for you to be able to visualize it in your mind and make some like at least two-dimensional pictures like this to guide your thought process, right? So basically here I have the inner radius, right? The inner radius, and right here I have the outer radius, right? And so if I just, you know, draw my washer again here on its lonesome, I usually do better with those. The thickness is what? What's that? Oh, did you say dy? Yeah, that's right. So we've got dy here. This is r in. And down here you've got r out. What's r out equal to? That's the easy one. What's the outer radius for every washer you can envision here? Radius of the outer circle, how far is that? It's always what? It's always 2, yeah. So the outside radius is always 2. The inside radius is equal to x, right? But that's not really helpful to us because we need to look at it as a function of y, because we're integrating over y here. See the dy? That means we're going to add things up in y. It has to happen. So how do we convert that x to a y? Well, that x is equal to what? It's actually equal to 2y. And sometimes I would call it the left x, whereas 2 is of course equal to the right x in this case. We've got the left x, we've got the right x. Keep in mind that this over here is the rotated image of that, right? So that's just for help visualizing what's going on. But I set up the calculation with just one of those. You'd be like, well, couldn't you set up the calculation with the one on the other side? Sure, you could, but you got to make a choice. I just think it's more natural to set up the calculation with the one that you're rotating. So, all right, so then what? What's the volume for this washer? Let me erase some of my doodlings. Oh, where I put my juice? Oh, maybe that's it. Yeah.
So on any test equation, do you have to draw like a 3D model like the washer and diagram how you diagram it now?
Sure.
Because I really can't draw like that. Sometimes it's confusing. So it's like, that's what I'm asking.
Well, yeah, I mean, of course, if you don't draw a picture better than mine, I take off points. But
Does the graph can the graph work instead?
I do require some sketch, but I am generous in grading. So
It doesn't have to be like that's what makes it.
you should try to find a middle ground between, like, I know maybe you guys, like, I had drafting in high school, all right? So like I have a certain background which helps me. And not all of us, some of us are more artistic than less. Like, I can't draw a face. Like, you could give me a week to draw a face and it wouldn't be anywhere close, right? My daughter can draw a face that looks like a real face, because she has that gift. But we could all at least get to the rudiments of technical drawing, right? Like making a basic graph and
I can do that.
the 2D thing is more important. I usually just, well, anyway. Sorry, I'm not saying anything interesting. Where was I? So, what's dV? Well, dV is the volume of the washer, right? So dV is pi times r out squared minus r in squared, dy in this case, right? So in this context, we've got pi times r out squared is 4. R in squared is, 4y squared, yeah? dy. So we might as well factor out the 4. We've got 4 pi 1 minus y squared dy, right? And to find the total volume, we need to integrate 4 pi 1 minus y squared dy. Now what should we integrate over? 1 to 2 or 0 to 1? Which one would make sense? How do we decide the domain of the integration for these kind of problems? Context, right? So we make a slice, we make a washer slice where? From 0, y equals 0, all the way up to where? See this right here is y equals 0, right? This right here, y equals 1. So that's why the integration bounds go from 0 to 1. And that's, to answer your question a little bit more seriously, why the picture is important, right? We need to draw this picture so that we can, come up with the bounds correctly. Well, that's my kind of integral. So that's just 4 pi times 1 minus a third, which is 8 pi over 3. There you go. So that one's considerably more pleasant than one of the integrals we tried to do yesterday, right? Yeah.
I'm sorry, why from 0 to 1?
because we're making a slice at y equals 0 all the way up to y equal 1. There's a washer at each y. So dy, whatever you write as your differential has to inform the integration bounds, because we're just adding up the volume of each infinitesimal washer over. Does that make sense? If I had given a different outer radius other than 2, we would have ended up with different bounds, but you know. I love integrating polynomials from 0 to 1, you know? It's like the most fun integral that there is. Well, maybe not the most fun, but pretty close. Let's see here. All right, so method of washers, and more generally, like just the method of slicing. If you've got a volume and you've got some kind of sort of axis that goes through it, and you can find a regular formula for the area of a slice, which is, you know, cross-sectional to that axis, then you can just integrate the area as a function of the axis coordinate, and there you go. And so we've seen that with washers. Last time we saw it with like square slices, with the square pyramid. We saw it with discs for the cone. All of these are kind of the same idea, right? They're all kind of the same idea. Even the sphere, we calculated the volume of a sphere or a cut sphere. Again, it was either discs or washers, right? There's another method though, and I think that, I'm trying to remember, was the example that Professor Schmidt had left over for us with the other method? I can't remember. It was washers? Oh, so still more the same. So it is time for us to learn the other method. Example 3. And so I will force the issue with an annoying example. Take, so here's sine, all right? All right, so let's take sine. Let's rotate area bounded by y equals sine x for, well, by sine x and x equals to 2 pi and 3 pi and the x-axis about the y-axis. Find the volume. So as you think about sine, we can erase what? We only need to think about which part of that graph. So, you know, full disclosure, guys, I gravitate towards using the method of washers. To me, it's more natural, but the method of shells does have its place. And we need the method of what's called cylindrical shells here. I regret the scale of my graph. I'm going to have to erase that. I see that now. Sorry, guys. Because I think I was over into the, oh well. I mean, it went in. It was off camera, but it was a beautiful shot. Let's see here. So let us pretend that hump of sine is like here. All right. Now that's not quite to scale, right? But all right. And then it would rotate to like over here. Let me make it bigger, actually. Sorry, guys. I'll eventually make up my mind what I'm doing here. That's kind of exaggerated, but it'll help me make the picture easier to follow. All right, I tried. All right, anyway. So if you can envision this, the volume we're trying to find here is something like, what is it? I mean, it's, right? It's like one of these, and kind of got, I mean, I can't draw it either, you know? But Yeah, it's exactly kind of like a pound cake or one of those like old Jello molds, if you've ever seen it, you know, something like that. What do they call it? A bundt cake.
Yes.
So what's the problem with washers here? If you were to try to use washers, see what happens? If you were to try to use a washer method here, the trouble is if you did like that, right? Both the inside and the outside radius would both be given by the, y equals sine x. So you'd have to use y equals sine x for both. How would you achieve that exactly? I mean, then you have to use like inverse sine. But you'd have to use inverse sine in a kind of sneaky, convoluted way. But after the dust settled, you'd realize, wait a minute, I'm integrating the square of inverse sine. Do you guys remember when we integrated the square of inverse sine? Yeah, I don't either. So that won't do. On the other hand, if we look at the method of washers, like this, shells rather, I'm an idiot. We do something like something like this. So it's, I don't know, I have a really hard time drawing these. It's a cylindrical shell inside this thing, right? If you look at the book, they've got some, perhaps better pictures in there. It shouldn't be all the way to the edge. It's inside it. So if you can envision that, then the question is, let me just draw the shell on its own. That I can do. So the shell, unlike the washer, has height that's finite, right? But its thickness is skinny. So something like that. What's the thickness of the washer? See right here, you can see it. The thickness is, this time, dx, right? It's dx. And excuse me. You can imagine taking this washer, listen to me, I keep saying washer. You can take this cylindrical shell, right? Cut it somewhere, yeah? Lay it flat. What do you got? So imagine taking this thing, cut it anywhere you like, and then lay this thing flat. You got a slab, yeah? What's the volume of the slab? That's easy enough to figure out, right? So the thickness is dx. And you've got this height here, right? And the radius, what's the radius? Well, we call that x, right? So if that's the radius, what's the length here? It's the circumference, right? So this would be 2 pi x. What's the height here in this example, actually? It's what? Yeah, sine. Yeah, sine of x. It's y. It's y, right? And so what's the little bit of volume here? dV is equal to 2 pi x times the sine of x dx. And that's for what? That's for, by assumption here, that's for 2 pi less than or equal to x less than or equal to 3 pi. All right?
Is that bottom diagram, the cylinder turned to the side?
Yeah, this bottom diagram is just this cylindrical shell laid flat. Like just lay it flat to see its volume. That's how I understand the volume of the shell, but Now I've got bad news. The bad news is that I have lured us into an integral which we don't know how to do. I mean, I know how to do it, but I don't know if you guys know how to do it. All right. How do you integrate x times sine x? Like, it looks like cosine would almost work. Let's try something. Let us guess. So we haven't done this yet, so this is a good exercise for us. Let us guess that the integral of x sine x has the following form. Maybe like some constant a plus bx. Well, let's forget about the constant. There's always a constant's not interesting, right? So let's suppose it has the form ax plus b times, I feel like a cosine x maybe. It might be in order here. Maybe it should be, maybe I'm wrong though, maybe it should be a sine x. Right? That seems like a relatively generous guess for what the integral should be. We've never done this, but this is a thing you could do. You could make an educated guess about the form of your integral, and then you can work out what your guess has to be. So if this guess works, what do we have to do? Differentiate both sides, right? And we have to be able to get what? We have to be able to get that x sine x is equal to the derivative of all this. The derivative of all that is a minus b sine x plus what? What we got here? C cos x, yeah? I got CC cos x, good job. So can you guys tell me any choices for A, B, and C that would make this work? Well, it looks like I chose poorly. It looks like it's not going to work, right? But if we had B was like x instead of a constant, that would be helpful. So maybe I should go back to basics here. And instead of guessing, let me like modify my guess. It's not going to work in its current form. Let's modify it a little bit. Let's try this. Let's switch it up a bit here. I think what we want is like, let's try like a, judging from the derivative here. Maybe something like bx sine x plus, I don't know, maybe c sine x, maybe that'll work. If we differentiate that, we get what? We get b times sine x plus x cosine x, yeah? And derivative of that is c cosine x. Oh man, I never moved the camera. It's unfortunate. If I gave this example on a test, I would just tell you the antiderivative that you need to know here, because this isn't a required part of Calculus 1. The proper technique to do this integration we're doing right now is called integration by parts. But I just like this example for shells, so I'm showing it to you. Like I'm sorry, guys. It's just what it is. So here, in order to get these equal, what do I need? Looks like man, that does not feel right. Dang it. It's all gone crooked on me, guys. Well, I know how to do it. Let me just do it the proper way. I'm sorry, guys. My brain's not working today. So in Calculus 2, we make this dv, we make this u, and we do uv minus integral of v to u. This is called integration by parts. So the u is x, the v is minus cosine of x, and I have minus the integral of v, which again was minus cosine of x. My du is dx. So we get minus x cos x plus the integral of cosine x dx, also known as sine. So the answer is minus x cosine x plus sine x plus a constant, I think, if I haven't done something stupid. If we differentiate that, differentiating that by the product rule gives me a minus cosine x plus x sine x. So the product rule makes this give me an x sine x and a minus cosine x. When I differentiate this, I get cosine x. So the minus cosine x plus the cosine x cancels, and we're just left with the integrand. There you go. That's the antiderivative. Sorry, guys. So we can use that. And we've got 2 pi, my antiderivative after a little bit of calculus 2. So that's the kind of precarious thing about these volume examples for this course, is if I'm not careful, I end up giving you guys a problem which requires integration, which is slightly above your pay grade. Now, in terms of the calculus course sequence, we're only like a week ahead. Literally, we're only a week ahead. But the trouble is that week is into calculus 2. Like, this is week 1 in calculus 2, integration by parts, yeah? So it's not too horrible of a thing to show you guys, but anyway, let me finish this thing. We'll go on. Let me look up my. I'll get my laptop out here and show you guys some examples that are not requiring calculus 2. Let's see here. So what happens here? See, I'm just using FTC2 now that I know my integrand. Again, if this was a test problem, this would be given to you. Right? I wouldn't make you do this. This would be given to you. And so that's 0. That's 0. Cosine of 3 pi is minus 1. Cosine of 2 pi is 1. So it looks like I get, this works out to 3 pi, and this all works out to 2 pi. So we've got 5, looks like 10 pi squared. There you go. All right. Let's see if I can find us some better examples. Give me a second here, guys. I did make an announcement with links to the things I'm about to look at here. So I'll hold off putting the screen down. I know you guys are still putting stuff. Ah. All right. Do 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 do. All right, I think. Can I put the screen down? Good. So this is the. Oh, I guess I probably should plug it in, huh? Come on. There we go. There we go. So this is the Calculus 1 website. As you can see, it features some of my art. Let's see here. So one of the things I have posted here is solutions from, I have solutions from Stewart's Calculus. I've got like, can you believe I used to collect like 40 homeworks in this class? I collected 40 homeworks in this class. Every day I'd collect homework. Every day. Look at that. See that? Homework 1, 2, 3, 4, 5, 41 homeworks. That's from this class. back in the day. I no longer have this will of fire. Let's see here. Your predecessors, they beat me down. I gave up. It's just too much of a struggle. So now you guys have homework much less frequently. But anyway, so here's some examples on the method of shells we can look at together. Hopefully it will be a little more productive. So use method of cylindrical shells to find the volume of a solid generated by rotation of an area bounded by y equals x squared, x and 0 less than x less than 2, y equals to 4, and x equals to 0 around the x-axis. So the bottom of the, let me use some sophisticated pointing here. Give me a second. So the base of the region that we're rotating in this example is here. The top is this y equals 4 here, right? We're going from x equal to 0 over to x equal to 2, and that whole thing is rotating around the y-axis, right? Now, probably this problem probably could have been done with washers also, if I had to guess, but doing it with shells just for illustrative purposes. And it's from section 6.3 in some edition of Stewart. That was the section on cylindrical shells. Anyway, so here's the cross section, the cross pic, whatever we call this thing, the profile picture of the cylindrical shell. There's a picture of it on its lonesome. The height here is not just y, right? Now the height's not y. The height is the difference of this y, the top y minus the bottom y, which in this case is 4 minus x squared. And the radius here is x again. And so I have to integrate from x equals 0 to x equals to 2 for this one, because there's a shell at 0 all the way out to 2. So, and as you can see, we don't need calculus 2 to do this integral, right? So I like the sign rotation problem because it forces the, it forces us to use shells. But the integration is admittedly inappropriate for this course, right? Inappropriate material. Shouldn't have that at Liberty. Anyway, so 7. Here I have y equals 4 minus x, y equals 4 times x minus 2 squared. That, my friends, is a parabola which bounces off the x-axis at 2, right? It opens upward like so. And so that's the one curve. The other curve is y equals x squared minus 4x plus 7, which I complete the square on, to see that the vertex of that parabola is at 2, 3. So the vertex of the parabola at 2, 3 is like up here. So that one also opens upward like this. And so there's a region between the two parabolas which is bounded, all right? And that is the region which is then rotated around the y-axis for this example. So here I work out the intersection points of those parabolas, apparently 1 and 3. Yay, book problems. Always have super convenient whole number answers for intersection points, right? This does not happen in the wild. Only this is brought to you by calculus books. Anyway, so the height of the shell here is the top y minus the bottom y, which in this case is the quadratic, the formula for the upper quadratic minus the formula for the lower quadratic, which works out to this. And then, of course, we've got 2 pi r h dx. We write that. And then we integrate. That's the method of shells here. Yeah. Let's see here. And the integral, again, it's pretty elementary, right? This is a really nice problem, actually. I don't know if I gave you any ones that are really that nice in the homework I just assigned. This one's also good. This one, because this one we're rotating around the x-axis instead of the y-axis. So let's look at this one. So here you've got area bounded by x equals 1 plus y squared. X equals 1 plus y squared is a parabola which opens sideways, right? And x equals 0, well that's the y-axis. And then of course you got y equals 1 and y equals 2, which are here and here respectively, right? So I've shaded, that's the region that we're rotating around the x-axis, yeah? And So I use the method of shells for this one. So the shell in this case kind of wraps around the x-axis like so. The radius of this shell would be y, and the height of the shell, I call it h, it would be 1 plus y squared, because that's how far it is to get from here to there. Right. Now generally speaking, if it was like this, you'd have to do like the right x minus the left x to find the height of the shell, right? It doesn't have to be just y. It's just y here, excuse me, it's just x here, because one of the base of the shell is at the y-axis, right? If the base of the shell was out here or something, then I'd have to take like the difference between xr and xl to find the h, quote unquote. Anyway, so then the infinitesimal volume is 2 pi y times 1 plus y squared, and why do we integrate from 1 to 2? Because we've got a shell from y equals 1 all the way up to y equals 2. So we add up the volume of all those shells by integrating, and there you go. All right, so up till now, all of my examples have concerned rotations around either the x-axis or the y-axis, right? Is there anything else we could do? Well, this one is the same as the last one. So this is again a rotation around the x-axis. So I mean, we just looked at that. Let me not talk through this one. Well, maybe I don't have any examples here on that. I might have to make one up. Let's see here. I would encourage you guys to look at this one too. This has really nice examples. I linked these in the announcement I made like a couple days ago. But if you look through here, there's some really nice areas bounded by curve examples. And I wouldn't be terribly shocked if some of your homework was actually solved in here. You know? Yeah? It's possible. So these are nice examples. I would encourage you to look over them if you're struggling at all with this material. Take 10 minutes to read an example here. See if you can work it out for yourself, you know? Oh, triangles. Triangles are not nice. Triangles are actually a pain, by the way. Unless you just break it back to like middle school geometry. All right. Well, let me put this away. I think that's... Hope you guys don't mind me doing that, because you know, there's some days I can draw cylindrical shells and there's some days I can't. Today is a day I can't. So let's just accept it. All right, so let's go back to just, we can use whatever method we want for the next example, all right? What if we had to rotate around an axis which was not the x or y axis? How would the method change? Any ideas? Here, let's try, come up with something here. Let me look at this following region. We'll make the, let's see here. I'll look at y equals to 1 plus the square root of x. And we'll say 1 less than or equal to x less than or equal to, oh, let's say 4. All right. And let's do the x-axis. All right. So this is, you know, this bounds an area, right? Let's call that area, let's give it a name. Let's call it R. So here's a picture of that. Yeah? Now, instead of rotating it around the x-axis, I want to think about rotating it around something a little bit more interesting. Let's rotate it around the axis down here, let's say. we'll make it relatively simple. Let's rotate it around y equals to minus 1. All right, so rotate around y equals minus 1 axis. Find the volume. All right. Now, I'm not forcing us to use the method of washers. I'm not forcing us to use the method of shells. Let's look at the problem and let's analyze what would be the better choice of technique here. Yeah? So this rotates down to, all right, so we got like what? Here's the rotated image of that, yeah? I guess if I was making a better picture, when I get to 4, what am I at? Square root of 4 is what? 2. 1 plus 2 is 3. So this is starting at 1. It's supposed to go to 3. I guess this picture should be something more like, oh, I guess I don't have room. Oh, my bounds start at 1. Oh, thank you. So it starts at 2 and goes to, well, I guess it's, well, there are many problems here. Thank you, though. Very good point. So that's not there, is it? Well, anyway, this is not to scale. We definitely need to put some labels to be clear, right? 1, 4. To be clear, this point is actually 1, 2, whereas this point up here, and I don't think this picture does it justice, right, is 4 what? 4, 3. I mean, maybe, I guess it should be like up here, at least, right? There, I feel better about it now. So then down here, anyway, I should get some graph paper or something, you know, but it's hard to swap out the whiteboard. So the point here is that we have this solid of revolution like this, right? Now, my inclination is to use washers. So let me show you how I do that. I would cut it like this. It's like here's a typical washer, and then down here, like that, right? So if I was to draw it sort of like sideways over here, so we've got y equals to minus 1 in the middle, right? So here's my inner radius, and here's my outer radius. You know, what's the formula for R in and R out though here? I'll do the easy part. What's the thickness? dx, right? Okay, so dx. But can you tell me what's the formula? What's the formula here for Rn? To be clear, this is the x-axis here, right? So what is the distance to the inner radius? Yeah, just 1, right? Now, if you said -1, the good news is you're going to square it in the formula soon, so like no harm, no foul, you know? But it is 1. And then how about the outer radius? Like what's this distance? Look at it this way. It's the sum of two things, right? It's the sum of this distance, right? This distance, d1, and like R out is d1 plus R in, right? You see that? What is d1 though? That's just the y, right? For the defining curve, the curvy curve. So like it should be 1 plus root x plus 1. So in short, R out is 2 plus the square root of x for this problem. Does that make sense? So, all right, now we can do it. We can set up dV. dV is pi times r out squared minus r in squared times the thickness, like it always is for a washer, because that's the area of the annulus times the thickness. That gives us the volume of the washer. So let's work it out. So we got dV is pi times r out squared minus r in squared times the thickness, which here is dx, right? But that is specifically pi. My r out was 2 plus the square root of x. We've got to square that thing. And then we have to subtract r in squared, which was, 1. That's easier. dx. All right, great. So let's see here. You definitely want to work this stuff out before you write down integrals, you know? This is 4. It pays to simplify your dV as much as possible before getting to the integration. So I have 4, because 2 squared is 4, and then I get plus 4 times the square root of x, because I get 2 root x and 2 root x in the multiplication of this. And then, of course, I get x minus 1. So let's see here. We really have pi times 3 plus 4 square root of x plus x dx. There we go. That is what we actually have to integrate from where to where. This is true for what? We have a washer from where to where? 1 to 4, right? All right, so here we go. The volume should be the integral from 1 to 4 of pi times 3 plus 4 times the square root of x plus x dx. These problems are nice. We get a lot of practice on polynomial integration, don't we? We get a lot. Let's see here. So we get pi, and then we got 3x plus 4 times 2/3 x to the 3/2 plus 1/2 x squared. Evaluate from 1 to 4. I did that. It's the 1/2 power, right? 1/2 plus 1 is 3/2, but then I'm dividing by 3/2, which is the same as multiplication by 2/3. That's why there's that 2/3 there, right? We've seen this a number of times, I think. All right, what do we got? We got ourselves a pi. 3 times 4 is 12. What is 4 to the 3/2? Let's simplify that. That's 4 to the 1/2 cubed, right? Which is 2 cubed, which is 8. 4 to the 3/2 is just 8. So let's look at it that way. So I've got 4 times 8 times 2/3. So I got 64 over 3 there. 64 over 3. And then plus 16 over 2, yeah? And then I've got minus pi times the lower bound, which is easier to do, because evaluation of 1 is easy. So I got 3 plus 8/3. I'll get out of the way here in a second. Plus 1/2. So what do I got here? I got a pi. Let's see here. I got 9 from 12 minus 3. 64 minus 8 is 56. 56 over 3. 16 minus 1 is 15. Of course, you could do this arithmetic a different way. That's just the way I chose. And then I think I'd like my answer to be in, looks like sixths, right? So pi 9 times 6 plus 56 times 2 plus 15 times 3, all divided by 6. Make a common denominator there. So that's like 54 plus 112. 54 plus 112 is 100 and, oh goodness gracious, 12, 160, 168. Still got 45 though. 54. 54. What's that? 211? Divide by 6? Does it simplify? So 211 pi divided by 6. There you go. Not what I would have guessed, probably. That was close. That was actually close. It was off the corner of the back table. Like that means it was close. Any questions? Let us work another problem. What if I took the same shape, but instead of rotating around the y equals minus 1 axis, what if instead I rotated around, I don't know, x equals 5? How would that go? So same shape as example, oh, I forgot to number my example, my bad. What example was this? Goodness gracious, 3, 4? Example 4 it is, all right. So example 5, let's take this same area, but let's rotate it around the x equals 5 axis. Let's see how that goes. All right, so example, where are we, 5? All right, so we got this handy dandy. Where did that thing start? It starts at like, I'll try to do better this time. It starts at 1, 1, right? It's all the way up here to 1, 2, and then that's supposed to be 1, 1. So 1, 2, 3, 4, 1. So basically it's something like this is where this is the region that's bounded for us, right? So again, we have y equals 1. Oh, wait a minute. No, I didn't have y equals 1. What did I have? It wasn't y equals 1 I had as the lower bound. It was what? I'm a dummy. It was this, right? There we go. So it was y equals 0, y equals 1 plus the square root of x, and x equals to 1, and x equals to 4. Those are basically my 4 bounding curves, right? And now I'm suggesting we go over here to, let's say, x equals to 5, and rotate it around that axis. What's that look like? All right. Now we could use washers or we could use shells probably here, but I just prefer washers. I'm not gonna sugarcoat it for you guys. I just like washers. I'm gonna use washers. If you guys can, if you're more bent towards cylindrical shells, then I guess I should have told you to register for a different section of calculus. But it's a little late.